A vehicle's braking system is the most crucial safety system available to the driver. It allows the driver to consistently and reliably reduce the vehicle's speed, avoid obstructions, maneuver traffic, and/or bring the vehicle to a complete stop. The braking system used by the Lausanne Motorsports team in their competition vehicle is designed to withstand higher temperatures and higher stress levels during its period of operation than a conventional vehicle. Our team has been tasked to design a complete hydraulic braking system for the Lausanne Motorsports team, staying within our budget, time frame, and allowed rules. Through the course of the year, our team has been able to surpass numerous challenges, the first of which being the communication and coordination obstacles due to the unexpected global pandemic. In the initial stage of this project, we were tasked with drawing up a comprehensive problem statement, outlining our stakeholders' application needs, prerequisites for each stated need, and approximate timeline for each delivery. Following this, we took into account design parameter thresholds given by the governing body, the FSAE. The most crucial design parameter related to the maximum force applied in the brake pedal box without component failure, and the overall four-wheel independent operation to improve redundancy and minimize vehicle stability compromise under braking. Again, clarifying our problem statements, we revisited all stakeholder groups, their relation to the project, and how requirements supported our current problem statements. Our design is driven by a modular lightweight topology to maintain the vehicle's competitive edge and also allow a system to be easily integrated with different parts or components from another system to be designed by the following year. We began material selection based on operation limit thresholds for each component. For the components with high operating temperatures, like the brake pads and rotors, material selection was driven by heat dissipation capacity, strength to mass ratios, and thermal expansivity. While for components hosting high hydraulic pressure, material selection was driven by strength to mass ratios, specific material strength, material flexibility on brake lines connecting to master cylinders, and pressure transducers. We began procurement sourcing our most critical components first. These are parts which their size and assembly location will directly influence the placing and selection of other components on the hydraulic circuits. With component selection complete, a fixed design topology, and material selection complete, our budget had now been approved, and our 2021 capstone project was starting to come to life. At this point, our hydraulic braking system was starting to take shape, and we were ready to begin a critical design review. We outlined 3 distinct design solutions to the proposed problem, each with their merits and drawbacks. We carried out a detailed design comparison analysis to compare each 3 designs driven by our stakeholders' needs, safety, cost, and time. We then selected our optimal hydraulic brake design based on these matrices. In our baseline design, we decomposed the entire hydraulic system into its core operational components, the first of which being the brake caliper. The brake caliper is a major component of the entire hydraulic system. It is responsible for slowing down the wheel through friction with the brake rotor. This component withstands temperatures above 200 Celsius during operation, with pressures ranging just under 7,000 kilopascals. Secondly, we have our brake rotor. This is the rotating component of the system fitting over each axle. The brake rotors are responsible for converting rotational kinetic energy into thermal energy. For this reason, the rotors become a major friction surface in our braking system and will withstand temperatures in excess of 600 degrees Celsius during operation. Optimal heat dissipation on this component has become a crucial concern in our design. Thirdly, we have our brake pads. Brake pads are a major friction component on disc brake systems. They are responsible for creating friction with the brake rotor as the piston from the caliper squeezes against them the rotating surface of the brake rotor. Material selection of these components is most crucial. It will undergo extreme pressure and extreme heat during operation. The next component in our hydraulic system is the master cylinder. The master cylinder acts as the heart of the entire hydraulic system. It is responsible for transferring brake fluid under positive hydraulic pressure through the brake lines to each caliper piston. Our current design makes use of a tandem-type master cylinder. This way we can have 2 independent hydraulic circuits with a single control. This adds additional redundancy in the event failure of one circuit. Our master cylinder is also fitted with independent hydraulic reservoirs and an attachable propulsion valve. As the master cylinder is the pump of the entire hydraulic system, brake lines are the transport unit of the entire hydraulic system. The lines used in our brake system will consist of a combination of rigid and flexible piping, with material selection currently set to stainless steel and rubber. The stainless steel braiding is used for improved cooling where possible, and rubber piping around the pedal box to allow dynamic pedal box positioning without brake line adjustments. As said earlier, a master cylinder is equipped with an adjustable proportioning valve to allow brake bias control as per stakeholder or driver needs. We make use of a diagonal circuit pattern for system's independent circuitry to reduce negative effect of vehicle weight distribution in the event where only one circuit is in operation. The pedal box can be seen as a user interface between the brake system and the driver. It is designed to withstand forces excess of 2000 newtons, and material selection is set to be checkered aluminum. To maximize the driver's mechanical advantage, our design aims to maximize the pedal ratio. This is the force acting on the master cylinder pistons divided by the force acting on the actual brake pedal. We have also selected a swing mount pedal box, which makes us able to exceed our force requirements with a lightweight aluminum frame and a high strength reinforced I-beam, forged pedal arms providing pedal ratios of 6.25 to 1. Installed brake lights are in accordance with the FSA rules, red in color on a black background, rectangular mounted as per 2021 competition rules. The brake light encasing will be designed with AutoCAD's 3D suites, and the circuit board is designed using Eagle suites. The pressure transducers are in series with the brake lines before each caliper. They convert hydraulic pressure into an analog value. Our current design makes use of Honeywell's MH series pressure switch, capable of sensing pressures between 24 kPa and 2700 kPa, with a maximum operating temperature just above 120 degrees Celsius. The brake over travel switch is an FSA requirement and added redundancy in an event of complete brake failure. If the brake pressure is lost, when the pedal is pushed, the pedal will travel beyond its normal range, with insufficient pressure being applied to the caliper pistons. The brake over travel switch will be activated, and when this condition is met, electrical power to the fuel pumps and the ECU will be interrupted and the engine will shut down. This switch is implemented as per FSA competition rules with analog components for additional system redundancy. As known, our design solutions are subject to inherent risk, benefits, and drawbacks. Our trade study matrix provided an effective way to identify the most acceptable technical solution amongst our set of proposed solutions. Our final design showed excellent heat dissipation capacity. The major property responsible for extruding heat from the circuitry is the use of braided steel hydraulic lines, along with the proposed sections of the vehicle chassis. Our solution also improved system redundancy, making use of tandem-type master cylinders for individual circuit control and a diagonal connection between each wheel. In the event of failure of one circuit, so this solution minimizes the effect on the vehicle's weight distribution under competitive braking conditions. Making use of a tandem-type master cylinder integrated with proportioning valves for each circuit also brings down the cost of the entire system. Our use of source components from improved FSA manufacturers also provides additional redundancy and improved modularity. Sustainability can be understood as avoiding or minimizing the reduction of our natural resources to maintain an ecological balance. In other words, meeting our needs in the present without compromising the needs of the future. Sustainable processes were a major concern and regarded as functional elements in every design phase. Through each design phase, we considered 6 interwoven factors in system design, which we can control. First of which was an initial analysis to see how each phase could improve the system's overall environmental friendliness. The second of which was a way to minimize costs of manufactured components. After minimizing costs of manufactured components, we strive to minimize energy consumption during component design, manufacturing, and operation. Manufacturing and production planning will be done between cutting and bending processes during pedal box fabrication. A fourth of which we strive to minimize waste of material in all processes. The use of wheel-wood manufactured aluminum fixed calipers provides a significant weight reduction on the driven wheels, which also provides a continual reduction in residual torque. This means the operational friction on the rotors when the brake is not being applied minimizes, and this in turn minimizes our wasted brake material and reduces the vehicle's overall CO2 grams per kilometer. Fifth of which was operational safety. During the manufacturing process, we will develop, promote, and apply safety standards to minimize any unreasonable risk as a result of functional insufficiency. And the last but not the least is improved personal health. Friction material deposits and their impact on our health has been a major concern in brake development over the last century. We took a team initiative as Renaris engineering students to specifically select brake pads manufactured only with the use of earth-friendly materials while maintaining our competitive edge. We made sure to exclude any materials made with parts of lead, asbestos, nickel, or any harmful ceramic fibers like antimony or trisulfide.